All right, I think we're going to go ahead and get started. So it's a real pleasure to introduce our speaker today, Russ Tedrake. So Russ is the Toyota professor at MIT in the Electrical Engineering and Computer Science department. And he also holds joint appointments in MIT, Aero, Astro, and he's a member of the Computer Science and AI Lab. So Russ received his undergraduate degree at the University of Michigan, and then his Ph.D. at MIT, working with Sebastian Sun, who's now our colleague here at Princeton in neuroscience. So I think many of you might know Russ from his work on motion planning and nonlinear control for underactivated robotic systems. He's done lots of work on flying robots, walking robots, and most recently on manipulators, and he's won numerous awards for this work, including Best Paper Awards at pretty much every major robotics conference and journal. What you might be slightly less familiar with potentially is his work during his PhD, when he worked on reinforcement learning, specifically actor-critic methods for learning leg and locomotion. So you have these really super impressive demonstrations on minimally actuated walkers, so learning to walk from scratch within just 20 minutes. And I remember as an undergraduate student, I watched a talk that Russ had given on this topic, and this kind of got me initially excited about this group, and then led me to his group for my PhD. And in some sense today, I guess we'll be coming full circle. So Russ will be talking about his work at the Toyota Research Institute, where he's the vice president for robotics research. And they've been working on really sample-efficient learning for dexterous manipulation. So this is a collaboration with Jerome Saltzer, who many people in the audience here know well. And some of the videos we'll be seeing are, I think, some of the most impressive, maybe the most impressive empirical demonstrations of behavioral cloning using these powerful generative models in the context of dexterous manipulation. So Russ, thanks so much for taking the time. It's a real pleasure to have you here.
Thank you, Ani. It was a real pleasure to get to work with him for his PhD, too. So, yeah, so this is, as Ani said, it's a slightly empirical talk compared to some that I normally give. We've got some, I think, a really exciting success in applying some of the diffusion models to real robotic manipulation. So I want to start by telling you about that sort of empirical success. And then I want to, depending on time, I want to tell you a little bit about how we're trying to grapple with what happened and try to understand a little bit more theoretically what's behind these models. Okay, so it's work primarily done at the Toyota Research Institute, but I'm going to start my story a little bit, including some of the MIT work that inspired it. So just to make sure everybody's still on the same page, AI does many things, but manipulation is still hard, right? So if we're in a robotics seminar, I don't have to motivate it too much, but I think we should dream for robots being more capable with their hands than they are yet today. And when I like to think about what dexterous manipulation means to me, it's not pick and place type manipulation. It's much richer than that and much more subtle contact interactions with interesting state representations involved and really beautiful physics involved. Okay, so we haven't seen robots doing that kind of thing yet, and I can't show you that one quite yet today, but that's what I want out of my manipulation system. So we started working on manipulation in earnest at TRI in a team that was called Dexterous Manipulation, starting in 2016. And it was really interesting for me to think about what could a team do at a place like Toyota Research that I couldn't quite do on campus. And one of the things that we could do was we could try to build systems at a higher level of maturity and just at a bigger scale than I could on campus. So we've been organizing our work around challenge problems, okay? And one of the first challenge problems we picked, this was actually, if you think what was happening in 2016, this is right when computer vision started really working. We could think about taking our perception, planning, and control stack, but start applying them to sort of objects we'd never seen before, or at least a wide diversity of objects. So we picked this problem of just trying to load the dishwasher really reliably. And it's sort of interesting to see what we did then, because it contrasts with what we're doing today. So this was the basic problem setup. We'd have C1, for instance, dump a pile of dishes and garbage, for instance, in the kitchen sink. And then the task for the robot was to basically load the dishwasher. And anything that was not a dish, it would discard to the right. And the mugs went on the top shelf, the plates went on the bottom shelf, the silverware went in the top tray. And the system that we put together here was state of the art for its time. It has a lot of really good motion planning involved. It has deep perception, recognizing plates and silverware and spoons and, and mugs, right? And it has some actually pretty subtle interactions. So one of my favorite was, for instance, having to pick up the plate, which was a pretty subtle interaction involving a lot of contact sensing and control. It would sort of reach in until it hit a force threshold. And to get this to work at a very high level of reliability, we were getting up into the nines of reliability with a pretty complex system at the time. That particular skill and others, the more nuanced manipulation skills like it, were designed with a combination of powerful simulation. That's a simulation on the left, of course. But also a very powerful engineer who wrote a very good state machine that it used his intuition, his robot whispering powers, and basically was able to design, after watching all the failure cases, a state machine-like algorithm that handled pretty much every case we saw for that sort of narrow problem. I mean, it was actually a surprisingly hard problem. Sticking a big kuka in the small kitchen sink and all the different places the plates could be in different varieties. It was actually pretty impressive how far that went. Okay, and a big part of that effort, we actually built up a very good simulation pipeline. So we've got state-of-the-art, contact-rich simulation that was underlying a lot of that tool, a lot of that research, and we continue to use that and benefit from that. And we were doing large-scale simulation-based testing, catching bugs in simulation, fixing them on the real. It's been extremely, extremely good. But it brought us to the point when we decided to sort of slow down on that project and think of the next grand challenge. Like we've invested so much on models, so much on simulation, that we said the existential risk to sort of this approach to the world is that there's a lot of things that we don't think we're going to have first principle models that are useful for. So what are we going to do when we have to start doing things where the physics simulator isn't the obvious go-to solution? And there's a number of interesting tasks in the home that we could have picked. Laundry folding is a good one. People talk a lot about tidying up or helping with tubes of toothpaste, or there's all kinds of things you could pick in the home that are hard to model in first principles. But we decided to sort of focus in on food preparation because it's just so easy to get diversity and richness and complex mechanics. For $5 at the grocery store, you get a huge amount of diversity. Okay, so it's interesting to then go back to our toolkit, and we have really powerful toolkit with a lot of work in simulation. But that's sort of by definition, we said that's not going to work yet. Interestingly, the simulation team at TRI has been chasing us every time we say you can't simulate this, and so and then we show a task that was hard to simulate. Then a few months later, they can simulate that, which is good. Not everything, but it chases us pretty quickly. Okay. Also, simulation-based reinforcement learning was not available immediately. My order was a little bit. And anything that fundamentally relied on state estimation, which meant all of my model-based control tools. If I had to say, what is the state of that pepper as I'm cutting it, then I'm sort of dead in the water. So that doesn't leave me a lot of tools. The ones that I would initially reach to would be, I could say, oh, let's invest heavily on learning plant models, learning world models, dynamics models, right? And we have been doing that, and I think that's a powerful path forward. But we also took note of some of the things that had been happening in direct behavior cloning recently, and decided to, based on some initial success, decided to lean into that and say, how far can we get with behavior cloning? Okay, so it actually started at MIT with Pete Florence and Lucas Manueli. We're doing work using some self-supervised features in a visual motor pipeline for behavior cloning. And these were the kind of demonstrations that I saw for the first time connecting camera feedback at high rates into a control system that this is just, it wasn't the first time it happened in the field. This was the first time I really felt the power of it, right? Was to see the robustness that came out of putting a camera image in at high rates. And all the things I was afraid were going to break that camera-based feedback, we were able to be very robust to that very naturally. Okay, so Pete and Lucas and Yunzu and their collaborators really changed my mind about things. This is an object that was deformable. It still had to sort of put the hat on the rack, and we could do it for any number of hats, for instance. Okay, so that was the initial project that made me realize how powerful behavior cloning and visual motor feedback could be.
Did they turn the hat upside down?
If I turn the hat upside down? I think the answer is sort of simple, is if you gave me examples of the hat turned upside down, then I bet it would work. And if you didn't, then it won't work, right, in that setting. So, and the tools have gotten more powerful, but the answer's still going to be in that direction. And all kinds of tasks, but what I have to really somehow convey is the level of robustness here is just impressive. You could come in any day, take off your shoe, put it on the table, and it would put it on the rack, and that was our shoe task. And you could push the shoe around while it was manipulating it, right? And this was just a very, very robust, when it was in distribution, a very, very robust system. And that changed my mind about how powerful behavior cloning could be. Okay, and I really do think that the most important part of that is that we are now closing feedback loops from images, and we were sort of ignoring RGB before, and we must not do that again, right? So, and of course, importantly, the feedback controller, which tends to be relatively small still, at least in those examples, is using a learned state representation. So I didn't need a deformable model hat, for that hat. I could just work with some learned representation, and that's a big, big deal when you're talking about these hard-to-model systems. So it really forced me to reflect on my core beliefs, right? I said it already. I must not ignore RGB anymore. It's just such a powerful feedback signal. Still to this day, I would say I don't love imitation learning, right? I think decision making is more than imitation learning. But I do think it's an incredibly clever way to understand the space of visual motor policies, right? It's like, it's a fast way to sort of explore that space. You don't need a model. You just need some demonstrations. You don't need an explicit state representation, not even to specify a cost function, right? That's an important one that comes up a lot, is that some of these tasks are just fundamentally hard to write a cost function for, right? Where if you just use the cost function being to demonstrate a human, then that's a much easier specification. Okay, so we've been exploring, and the best thing that we have so far is this, based on this diffusion policy work, which was, so Sharon's star student, Chung, came to TRI for the summer, and just changed the way we're doing things, right? So it's been a fantastic collaboration with Sharon Song and the folks at TRI. And it came out with this diffusion policy. So nowadays, the tasks that I have been saying, actually in my underactuated class or my manipulation class, I've been saying sort of for years that I have no idea how to make a robot spread peanut butter on toast. Or I said tying shoelaces, I've said peeling potatoes. I had sort of a kind of a list, buttoning a shirt. And they have basically systematically gone through now and done every one of those, except for the tying shoelaces, and that's because the hand's not dexterous enough in this set of robots. Okay, so this is not peanut butter, it's chocolate hummus, which I didn't know was a thing, but chocolate hummus on toast, turning pages of a book in a very subtle way, right? Pouring berries out. I could have picked any number of these. The behavior cloning is working incredibly well now, and I'll tell you a little bit about that. Okay, so it's visual motor policies. They have the same sort of visual motor policy robustness that we've seen before. So they're using the cameras at relatively high rates, right? But they're also solving tasks that I might have thought were natural or easy. So this is, when I see this, I think of Neville Hogan, and he's and all the force-based interactions that go into doing that. You're operating on a constraint manifold now from the egg beater, okay? But that actually works surprisingly well.
But where is the
There's a couple cameras. So the camera we see is not the camera that the robot's using. There's like 3 cameras pointing down at the table.
Okay, they're not on the end effector.
There is also one on the end effector, one on each end effector in this case. That's true. We just fuse them all in. Yeah. I think the more important ones, I think, in this example, are the remote ones. And then, so Naveen one day, just maybe to surprise us, he said, you know what, I'm going to go back and I'm going to do dish loading, just because you guys spent like 3 years on that. You worked really hard and you got some level of robustness. And in about 3 hours, he did something that was a sort of comparable task with some of that, pulling the plate off the stack, whatever. And Siwan, who had spent all that time, sends in a note around. He said, I think it's as robust or more robust than what we did in 3 years before, right? So, something's happening here, and I think we all should, we need to sort of, as a community, understand what's happening. It happens, so it really, this is yesterday. I just went on Slack and said, okay, what happened yesterday? And this was the one that came out yesterday. Just an interesting, unrolling a mat, right, bimanual. So roughly the recipe is 50 demonstrations in, train overnight, and then you get a policy out that'll do these kind of rollouts.
This is like 50 on this mat, or?
Yeah, so in this case, I suspect it was 50 on this mat. In other cases where the task is a little bit easier, we would have more diversity in the types of, in the like multiple potatoes or whatever. This one, I only grabbed it from Slack, so I didn't actually know what exactly he did, but I suspect it was just that mat. Yeah. Okay, so I think many people are familiar with denoising diffusion. Let me say a few words about it just to make sure people are on the same page. The basic picture really, so it has a rich history in score matching, and you can understand it through the lens of probability for sure, but the simplest explanation, which is actually what people are implementing in practice, is that you take some image, in this case, in the initial DDPM sort of work, you take an image and you add noise to that image to bring it closer and closer to a random image, okay? And that's something you can do easily on any image. And the clever trick then is that you use that as sort of a self-supervision to train the reverse diffusion process. So now you say, given a noisy image, I'm going to try to slowly move it back towards the original image. Okay, so it's an easy way to make lots of data, and without explicit negative mining, for instance. It's a sort of a self-supervised pipeline that makes a lot of sense. Okay. The interpretation that I like, and by the way, you can condition the denoiser on additional inputs. So if you wanted to, for instance, say, I want a cat, right? You could condition it on a clip embedding or something like this and ask for it to generate a cat. And the way you would generate a new sample, of course, is you just put in a new random image and then you denoise it towards a proper image. The way I like to think about these things is actually there's a deterministic interpretation. Frank and Chen Yang have been pushing this, and it's helped my thinking about it. So if you take seriously the manifold hypothesis, which people often talk about in the diffusion learning or in manifold learning more generally, so maybe there's some manifold in the high dimensional space of possible images, right? And the job of the denoiser is just to push you back onto that manifold. If you take that seriously and say that there's some manifold in the high dimensional space, then the interpretation of diffusion is that it's roughly learning the Euclidean distance to the manifold, and that the denoiser is learning effectively the gradient descent update that's pushing you back towards the manifold. It's actually a projected gradient descent back onto the manifold. Okay, so and then you can imagine conditioning on something to steer that path to a different part of the manifold, or doing classifier guidance, or any of these other sort of approaches to shift where you land on that manifold. But maybe the heavy lifting, and possibly the thing that's changing the optimization landscape in good ways, is that you're learning not just the manifold explicitly, you're learning some big quadratic bowl pushing you towards the manifold. But I also want to think about it a bit from the lens of control, right? So what we're learning here in these diffusion policies is a dynamic output feedback policy, okay? So in our case, I'll tell you the exact transcription here, but in our case, the input is a history of observations, okay? And the output is a sequence of future actions, okay? So the diffusion policy is going to be an autoregressive model with forecasting. So it really takes this short history of observations, okay, here, and then and history of previously applied actions, okay, and it's going to predict future actions. So from the view of the control policy, the observations are the the input to the control policy, right? Okay, good. So H is the length of the history, right? And P is the length of the prediction. And it's interesting. You would think maybe that you'd only need to predict the next action and then just run this on every step. But having a forecasting model has had implications. I mean, it just definitely works better, unquestionably works better, and for somewhat subtle reasons. And I'll tell you at least one of those sort of subtle reasons in a minute, okay? But it seems to be dramatically better, especially in multimodal behaviors, if you predict a forecast of future actions. In practice, we predict the next 1.6 seconds of actions that the robot should take, and then we execute about 0.8 seconds of them, and then we plan again, but we're always forecasting ahead. Okay, and then this conditional denoiser is what's producing that forecast conditioned on the history, right? So the denoising diffuser can be warped into a control problem without too much imagination. The way that looks sort of architecturally is that we're going to take our history of observations, which are most importantly the cameras, although we also throw in the robot actions or the robot states. Okay. We have for the single task case, we have just a standard ResNet pre-trained on ImageNet coming in. The whole thing, after you go through the denoising diffuser, the whole thing is 150 million parameters. It costs $150 to train a new skill. Okay, we're using UNets because UNets have been working incredibly well for diffusion, and they worked well for us also. We explored a few other architectures, but this is the one that's working the best. Okay, so here's one of the first tasks that we tried to sort of make sure we were understanding what was happening with. This was this push T task that Chung worked on his first summer. Okay, so I think the task is clear. The human is trying to give demonstrations first to push the T back to its known location. And then the way the picture of this diffusion, taking a random image and then denoising it down to a real image, the way that looks in the robot action space is that if I take a frame of this image or a small history of images, then initially the robot's going to have a random set of actions coming out. And if I denoise it, then I expect that random tape of future actions to sort of become a consistent set of actions for the robot. Okay, so it looks something like this, right? A random set of actions becomes into morphs down onto the manifold, if you will, to a coherent path that the robot then executes for the next couple seconds, and then, or 0.8 seconds typically, and then on to the next one.
Can I just ask?
Of course, yeah.
There's a clip where, I guess one frame where it just looked like the actions went that way and then back.
Yeah.
Is it generally the case that actions, that looked sort of wrong to me, because if you did that, you would just lose contact with the team. I think that
one right there.
Is it generally the case that actions in the future are not that good, or am I just misinterpreting?
It's fair. It's fair. So we don't normally in the higher dimensional problems visualize them as clearly. So the most experience we have is seeing the first 0.8 seconds roll out. But my distinct impression is that they're coherent for the whole 1.6 seconds, right? And I think that's essential in our understanding of it, is that predicting farther into the future is actually what's helping us deal with multimodality and things like that.
But I guess what was going on in that?
Yeah. So why was it sort of predicting that it could go back? I mean, that could have been a coherent action, but I agree it looked a little funny. Yeah, I don't know. I'm going to have to go back and look at that now. Yeah.
So Russ, one
Sure.
of the things you're showing us here is that it's a closed loop system.
Definitely.
That makes a big difference than running open loop.
For sure,
Yeah.
yes. So it is a little bit more open loop than I would like. So for 0.8 seconds, it's effectively, I mean, it's okay. Let me be careful. So it's still sending commands to a low-level feedback controller that's doing a lot of things down at the so it's not sending torque commands. It's sending endpoint commands through an operations-based control, and that is, I think, also essential to the success. If and we're working on improving the speed of the denoising, right? So if we could run it at higher rates, we would. So it's still a little bit more open loop than I'd love. Yes?
Why 0.8 seconds, why not longer?
Yeah, so why 0.8 seconds, why not longer? So I think part of that is about the timing it takes to do the denoising. And I think new work, like Frank's work, has actually showed us that we can even further decouple the denoising process from the noise generation process. So we could, for instance, take faster steps to get down to so there's things like that. I think the 1.6 seconds, I think 1.6 is a little arbitrary, but it needs to be relatively long during relative to the time constant of your behaviors. You want enough time for actions to evolve, the images to evolve and stuff like this. So I think if it was too short, you would lose some of this sort of multimodality that I'm about to show. Yeah.
So is the diffusion model sort of essential here, given the same training data? What if you use some other ways of fitting the essential conditions?
It's a great question. So yeah, is the diffusion model essential? I've got a slide actually that'll speak exactly to that. So let me, I'll answer that in just a minute, and then if I don't answer it well enough, we can ask. Okay, so one of the reasons we liked that task and used it to sort of study what was happening was that the human demonstrations that you get on that task were naturally very multimodal. And this was something that was happening, of course, in a much more subtle ways on all of the tasks. We were seeing the difference between whether an expert demonstrator could give the demonstrations and a non-expert. Was the biggest difference maybe was that the expert knew to not give multimodal demonstrations, okay? And in this one, there's just an obvious symmetry that was just visible and clear, okay? And the diffusion policy was able to somehow capture that multimodality, which is actually a very subtle thing and gets back to a little bit of the points we're just making. So Max Simchowitz, I think some of you know, has been thinking about what the heck just happened in that case. So many of you know that in imitation learning and behavior cloning in particular, you tend to worry about stability, right? Because you don't want your rollouts to walk away from the data and then you go out of distribution. Okay, so you'd like to have some notion of stability. But we also have multimodality. So we need to be able to go left or right around the T or left or right around some obstacle, right? And those things, by a lot of notions of stability, are in tension, okay? So Max has been doing work to understand how this forecasting model and chunking actions in the past gives you a slightly different space to be operating in, and the definitions of stability can hold, and it is consistent to be able to take observations that even in state space are overlapping, but end up taking different coherent multimodal behaviors. So stability and multimodality need not be at odds given the forecasting models. Okay, so people have been doing behavior cloning for a while. Andy's been doing it incredibly well. Also, I tried to put up a Princeton reference. I love Andy and his work. And he gave a behavior cloning talk at MIT not too long ago, and he was talking about, make sure you collect your own expert data, don't trust anybody else to make it perfect, avoid no action data so your policy doesn't just sit there. That one might still be true. Is it not working? Collect more data until extrapolation becomes interpolation. I mean, that's true of all machine learning. I think that's probably still true, but we've been getting away with a surprisingly small amount of data. Train and test on the same day because your setup might change tomorrow. That's, I think that is true that that's just not enough data. But although I agree with everything said here, we've seen success beyond that list, right? So the denoising diffusion models have high capacity and great performance for sure, but somehow we are seeing remarkably good rollouts from a remarkably small number of demonstrations. Typically 50. If we're going to give a demo the next day, then we maybe do 100, just to be clear. Yeah, careful.
Since I'm new to behavior coding, I
Sure.
hope this is not a totally crazy question, but there's a lot of art in teaching somebody to do something and giving examples, right? So that idea that there's an expert giving demonstrations. But is it possible to do, like, give 20 demonstrations, then see what the robot does, and then give more? Like, that's how you would train a kid.
Right.
For example, is to see, like, did you miss something?
Yeah.
The distribution here, it feels like the person who is demonstrating actually has to be pretty perfect in a weird way. They have to anticipate in one shot.
I think that's a very spot-on observation. So why would we give 50 demonstrations, stop, train, test, and not have a much more interactive loop? I completely agree. The whole team wants a more interactive loop, but it takes a couple hours or a couple GPU days to train these things.
So it feels.
So right now, today, we're in a mode, sort of forced to be in a mode where we train. You know, we get in the groove. We give our 50 demonstrations.
Yeah.
We typically just batch up the job overnight, come back the next morning, and roll it out.
I just wonder if, like, you might get even more amazing performance from 50 if you're allowed to train.
No
in
question.
batches.
No question. I think, so let me speak to that. I think, first of all, if we do see failures the next day, then there is a sense that we can add a few more demonstrations, and we typically can patch up any holes that we've seen. So I know that is true. I wish it was a faster loop. I think, and we've stopped requiring expert demonstrations, and that's one of the things that's allowed us to scale now, is that it used to be that only a few people could give these demonstrations. Now we have we pretty much invite anybody who wants to come in. We just tell them a few things about how to operate the robot, give them a little practice with the teleop system, and then they're able to give demonstrations. And if you were to come in and visit, you could even try to be creative. As long as you pick something that's like a 2-finger gripper can do it, and it won't occlude the cameras too much, you could bring, someone brought in a dustpan and like started sweeping stuff, that works, So we've gone away from the experts and towards the novice demonstrations, but we do tell them a few rules. Well, not rules, but just things to think about, which is, first of all, if you fail, don't stop the trial. We want that data too, because we want to, and just go ahead and keep recovering from that failure whenever possible. That's some of the best data, okay? And even we will say sometimes you'll intentionally try to fail just to show the recovery. One example of that, we had a flipping pancakes, okay? So we said just a couple times, why don't you airball the spatula over the pancakes, just so there's some examples of kind of going back and going around and under, because you don't want to be completely out. If you just miss the pancake once, you don't want to be completely out of data, out of distribution. But a very few number of sort of heuristics like that go a really long way. Yeah. So the ability to deal with multimodal non-expert demonstrations, there's lots of ways to deal with multimodality. So I think the categorical distributions work really, really well. I think there's a little bit less when you're doing continuous distributions. We struggled with some of the more, the other energy-based models. We tried very hard to make them work, and they didn't work as well for us as diffusion. There's a very subtle thing about training stability and consistency. Just the fact that we dialed in our hyperparameters and we haven't touched them for months makes a huge difference on the ability to keep growing with this. The fact that the outputs are continuous and high dimensional, right? So, like the RT lineage is putting out discrete actions, and I think the authors say that's not a big deal, But for me, I'm like, that's a big deal. I don't know. It feels like a big deal. The action trunking transformers from Chelsea Finn's group, I think this is the Aloha work. I think that could work too. So to answer your question, I do think transformers could work too. There's a couple reasons. These are some of the reasons that I like diffusion. One of the most important ones to me is that there's really solid foundations of mathematical foundations for diffusion, and I think where transformers are a little bit, you could maybe disagree with this, but I feel like transformers work partly because of their complexity, whereas the diffusion, if I take the case where I've got a linear plant and demonstrations from an optimal LQG actor, then the denoiser sort of simplifies down to like roughly learning the Kalman filter. You know, and I can understand, there's sort of like beautiful asymptotic behavior in the simple case, which gives me hope that I can understand that case better and push those results back up. And I feel that less, maybe just because I haven't worked with transformers as much, but I feel that less in the other case. Yes?
So I guess this model is not guaranteed to produce feasible actions in the sense that it's ignorant about the physics going on, and it's solely learning from demonstration, just input and output. But how do you
That is true.
handle the
So
usability and safety?
okay, yep. So I actually, I think that's almost next. Yes. So the reason it's okay that we're putting out potentially, bad actions and what's our safety case is because it's built on a tower of strong enabling technologies, right? So maybe the first one, I'll go slightly out of order, but I'll get to yours in just a second here. So the first thing is not only a teleop interface that we like, but also one that has haptic feedback. So for the egg beating task in particular, if you don't let the human, so haptic means the human feels the forces that the robot feels, right? If the human cannot feel those forces, then turning that crank is extremely hard. You almost get jammed, right? But as soon as you give humans the ability to feel that force, then it's just very easy and you can go quickly through, okay? So that is an important enabler for this. This is to your question here. So the actions that come out of diffusion get sent to a controller that is a more classic operation space control, but it's done really well, and it's going to protect us from hurting the robot, right? So this is the human trying to make the robot slam into the table, and it's refusing to do it, right? So there's a bubble of protection that's between, even self collisions. It's not going to let you do anything like this. So we have. That's how that's our safety case, if you will. Okay, and there's also actually some really nice visual tactile sensing. So some of these tasks are qualitatively better if the robot has a camera in its hand in order to see the forces that it's interacting with. So for instance, actually the flipping up the pancakes, if you just started putting perturbations and you moved the height of the table, then occasionally the robot that didn't have tactile sensing would airball over the table and wouldn't really know the difference. But the one that had the tactile sensing had a sense that you don't push forward until you feel some contact, and it would actually reach down, make contact, and then go much more reliably.
So there are load cells?
It's actually not a, so the Panda is has joint torque sensing, so we have some of that, but we're not using that explicitly. This is just a big bubble, okay? It's an inflated silicon membrane. When you grab something, it deforms visibly, and the deformation on the inside of the bubble, we have a pattern, and there's a camera, actually a depth camera, that's watching the deformation of the bubble, okay? And you can now, geometry in the camera is force information. Even shear and torsional kind of information is available just by the visual camera image.
And everything you do is position control? There's any compliance control?
No, it's all through operation space control. So we do have, think of it as a very low gain joint stiffness control, I think is probably the best way to think about it, right? So we have forward models that are canceling out the gravity terms so that our gains can be nice and low. And we are sending position commands into that. But when we touch unexpected things, the robot is compliant and willing to sort of go with the constraints. Okay, so now we have this pipeline that seems to be able to eat whatever data we throw at it, and of course we're trying to scale that up. So, we're doing demonstrations every day. We have now, engineers that are coming in and ops people that are coming in and giving demonstrations with very little training. We hired our first full-time robot demonstrator recently, right? And so the race is on. Let's see how many skills can we train. I talked so far about training one skill, but of course what we want is sort of a few-shot generalization to new skills. And we're already doing that. But I would say that it's a little too raw for me to put like learning curves up I was telling Ani before that we all want it to be true so much that I want to be super careful when I say it is true. But the initial promise looks really, really, really good. So we have language conditioned policies where we take the data from many skills and condition them on the natural language task and then watch the performance even on the original skills improving. We don't expect our robot engineer to generate ImageNet size data. But I think there's lots of lessons we've seen, especially going through language, of transferring and combining with the internet scale data, and we're seeing some initial success in that direction. But I do think there's big questions about how we feed the data flywheel. What are the scaling laws that people are still just getting their heads around? Right? We don't know how many skills are we going to need to have our GPT moment for manipulation. Right? I don't see an immediate ceiling. I'm sure it's there somewhere, but if I just kept putting more and more skills and making the model bigger and bigger, I cannot tell you what I think would be the first thing to break. Right now, it's going to cost a lot of money and time, but I don't see an immediate place where that stops working. So I do think there's something deep happening here, right? I do think manipulation, I've always said manipulation should be easy from a controls perspective. It's not like at the boundary of stability. It's not at the boundary of control authority. The tasks are relatively easy, but they're visually extremely complicated, right? They're probably low dimensional. And we've had a hard time seeing that, but it seems like it must be true for these things to work. And I do think in those kind of regimes, memorizing things can go a long way. I don't know if it goes the entire way, but I think, we'll see. I believe now that you could make very useful robots just by memorization. I might have said that even years ago, but I'm visibly convinced now, right? So it's a big question, right? And if we really understand this, could we do the same thing via principles from a model? Or will control go the way of computer vision and language? I think that's a big question, right? So a lot of people, and maybe even Ani in his introduction, sort of asked me like, oh, have you thrown in the towel and now you're just doing generative AI? And no, let me say clearly. So I think, I think some of us believe that there's a few truths in control, right? There's a few things that must be true, and there are many tools at which we can sort of inspect those truths, right? And I think this is a new tool, and I love looking at it through this lens. I think models give me another tool, and I will spend a few minutes at the end here talking about some of those other ways that we're trying to look into that window and learn from these results and connect it to our model-based tools. So if I did have a good model, I think the equation would change. I could still do behavior cloning, expect that to work, but maybe I could pay less demonstrators to do the work, right? And get similar success. There are core challenges for that pipeline, right? So we haven't done like the model-based control that Ani did when he was in his PhD, and that I have continued to do. Has not firmly addressed control from pixels. Control through contact, even though manipulation should be easy, we often write down models that make it like infinitely hard. Okay, and I think we've learned a lot from RL recently that maybe the limited specifications we've given in some of our classical modern, it's modern control, but optimization-based control might not have been as rich as what we've seen being successful in RL, right? So I think the most effective approach, if I did have that model today, would be, let's say, do RL on privileged information and then do teacher-student. So you've seen successes from that. For instance, the quadruped locomotion world has caught fire based on training in Isaac Sim and then deploying in the Alps, right? For instance, and I think that's an extremely powerful pipeline. Another lens by which we can understand these truths, right? I forgot to hit play, and we've been playing with them too. So, for instance, one of Poolkit's students, Tao, came over and was doing dexterous manipulation and peeling, trying to do some of the similar tasks at TRI over the summer, right? And showing some, pretty awesome results. It's a harder pipeline to go through. I mean, I cannot say that this took three hours to train. That's 3 months of work to get that kind of thing. So, but let me just tell you some of the lens, why I think optimization and control still matters. And I'll focus in I could tell you a story about any one of those, but let me focus in on control through contact. It's been a love of mine for many years. And just even understanding, I'll just say a few things about understanding RL for control through contact, okay? And again, partly picking up on one of Mac's contributions to our group, thinking about the role that RL has done in playing with contact. So in just a few words, so why is contact hard? Okay, control makes it look hard because we say that we have a beautiful, smooth, continuous dynamical system, and then at the moment that the foot hits the ground, we have a discontinuous update, and then we have another beautiful, smooth, continuous system. So these are hybrid dynamical systems, and in the worst case, that is just like a barrier that, you know, this mode could be completely different than this mode, and it's, you know, we have complexity results saying how hard that problem is. Okay, now we do actually have discontinuities in the real world, but they're not as common as you would think. If you think about actually not just the continuity in the one-step dynamics, but in the actual rollouts, then some of those are like the heel hitting the ground are actually more benign than you might think. But there are some real discontinuities, like if you drop a ball on a wedge and it could go left or right, then that's clearly a real discontinuity. So how is RL dealing with this, right? Even if you have a soft contact model, of course, that makes your discontinuity in solutions look a little bit more like this, but that's just hiding the problem in a stiff differential equation. That's not actually fixing the problem. Okay, so that seems like that should be a problem for our optimizers, right? Because when you have non-smooth optimization, then even gradient descent can get confused pretty fast. So it's an interesting question, like why is that not screwing up RL? Okay, and when you think about non-smooth optimization, there's a natural idea. Let's just say, what if we smooth our discontinuous objective? Okay, so take some random loss function that happens to be discontinuous. If the decision variables are x, the cost function is f of x. It's discontinuous, and I'm just going to smooth that out, for instance, by maybe just dragging a Gaussian kernel across the loss landscape and just smooth out my landscape. Okay? So for instance, if I had the Heaviside function as my loss landscape and I just took my probability kernel and I drag it through, then I could get something that looks like a nice, smooth objective function. So it turns out, I think that the right way to think about what's happening in RL is that it's actually doing that for us, that some of the sampling and stochasticity that's happening in RL is actually having a smoothing effect on the potentially discontinuous landscape. So if you take your original RL objective and you ran completely deterministic rollouts and no exploration in the policy, then you're going to have discontinuity. But if you start taking expected value over stochastic rollouts, even if the noise is being put in the outputs of the neural net, then some of our original discontinuous problems become nice and smooth again. Okay? So I think this is sort of one way to understand, maybe through the lens of models, of what's happening well in RL and learning. And then, of course, you could take that idea, and that's sort of a way to understand RL. I'm just speeding up a little because of the time, but and you could put that back into a classical model-based control approach and get some pretty good results. So basically, things that people, rich contact tasks that you might have associated as only being possible from RL before actually fall out pretty naturally with just traditional model-based controls when you bring some of the smoothing ideas that were inspired from understanding RL back into the model-based pipeline. Okay? So that's sort of one class of ways that we're thinking about trying to use models and learning together. Okay, but I don't think it addresses the discrete decisions. I think that's sort of a local smoothing of the loss landscape. If there's discontinuities, then we'll kind of round them out. But if there's still discrete decisions that need to be made, am I going to go left or right around the obstacle, then I don't think RL has, trajectory optimization with smoothing doesn't solve that problem. I think we need something else, or we need to understand why RL is solving that better, for instance. And we do have some new machinery. I think there was a very important point to make there, but it's gone. We have some new machinery thinking about this sort of mixed, discrete, and continuous high-level decision-making using models, but it's actually coming back and informing the way we think about RL too. Okay, so let me just tell you that in a few slides, even though it's a long story. So there's work with Pablo Perillo, for instance, and Tobia Marcucci and Jack Umenberger. We've thought about taking the original shortest path on a graph problem, which we could think about with RL, we could think about with dynamic programming, we could think about it as a linear program if you want. Okay, just finding the shortest path on a directed graph, a weighted directed graph. Then we're going to make a small modification to that. Every time you pick an element, every time you visit a vertex in the graph, you're allowed to pick one element out of a convex set. So that's what I mean by graph of convex sets. And you're allowed to choose the edge length based on the continuous variables. Okay? Then that's a simple problem to write down. It turns out that it has a very nice optimization backend. So it turns out that you could write that down with a mixed integer optimization framework, okay, but it has very tight convex relaxations. And I see Amelia up here. So the way that Pablo said it to me, which I think is the most insightful, right, possible, he says, there's basically one thing people know how to do in order to tighten a convex relaxation. You multiply constraints together. That's almost always the trick. It's like the one trick, you know? And so the reason that the graph of convex sets has such a strong convex relaxation is because there's a few constraints you can multiply together, which give you a lot of power. In particular, the integer constraints on the binary variables multiplied by the local continuous constraints. Those are the ones you want to multiply together. They have a beautiful sparsity, so you don't actually, a lot of times when you multiply constraints together, you get a bazillion constraints. But here we're getting a very small number of extra constraints that add a lot of tightening power. And the extra thing is that normally when you multiply like even linear constraints together, you get quadratic constraints out. So you've bumped the complexity class of your problem. Here, because some of those variables are bounded above 0, we actually can use perspective functions to keep the complexity class low. So we get to solve this problem without jumping to SDP. We stay in an SOCP or better formulation, and we get really efficient and really tight convex relaxations for problems that can be cast in this sort of graph of convex sets framework. Now, how the heck am I going to get back to contact and reinforcement learning with that? Okay. In the short term, that gave us new approaches to motion planning that are finding good plans faster than sample-based planners. Okay, let me just show you some of the. So this is a bimanual, so 14-dimensional state space problem where we're trying to find collision-free plans, and we sort of intentionally put it in like it's playing Twister with itself kind of in configuration. Okay, and we've done a convex decomposition of the configuration space, which is a hard first step. But once we've done that, we can now find beautiful collision-free motions with convex optimization, right? In a problem that, you know, if I saw that before and you said I was using convex optimization to do planning, I'd be like, okay, that's lying probably, you know, but it actually works beautifully well. Okay, and it works on real robots. We can plan complicated motions even through multimodal motions. It had decided what order to pick up the mugs and what timing. Okay, and it's working on real robots. This is a company that's trying to do food preparation and is successfully doing food preparation, and they were using a PRM that they'd worked very hard on, but time was money, and they tried out GCS, and they were very happy that it's solving these problems better. Okay, but actually the graph of convex sets, so that was a transcription of a robotics problem into graph of convex sets, but the connection to RL is actually fairly deep. So I was talking to Ben about it a little bit earlier this morning, but it turns out that the machinery of graph of convex sets gives us the way to parameterize piecewise value functions over the sets. And even the original convex relaxation has a dual solution that looks like it's pushing up on a value function. And there's a lot of good connections, I think, that will allow us to do sort of value functions on a graph of convex sets, and I think understand some of the combinatorial complexity and bring some of the combinatorial tools back in. For instance, in my last minute here, I'll just say, you could do planning through contact. So this was the original diffusion policy example that we liked to use, and this was them giving human demonstrations of that. And actually, Chung came to me early on. He's like, well, you do planning through contact, so giving these demonstrations is really hard and annoying. Can you just give me a planner that does this? And I was like, no, I can't do that. We've been working on it for 20 years, but no, I don't actually have a planner that can just solve that problem. But now we finally have a planner that can just solve that problem. So we can solve problems like this by formulating them as graph of convex sets, writing all the complementarity constraints of contact with their convex relaxation, and finding solutions with convex optimization that solve this problem to global optimality almost always. So I'm very excited about that. And I think it has a lot of room to grow. And we can solve some other manipulation tasks too. OK, so dexterous manipulation is not solved. But progress is super fast. And I think the visual motor policies are a huge difference. And the diffusion policies are working really, really well for us. We're training one skill with about 50 demonstrations. And this multi-skill thing is our path to foundation models. I really think that the field needs deeper, rigorous understanding of what's happening here. Some of the bridges that we're trying to build go through randomized smoothing and graph of convex sets, but there's much more work to do. And the code is open source. I'll take any other questions. Yeah.
All right, I think we have a few minutes for questions.
Sure.
Suppose you wanted to, oops, sorry about that. Suppose you wanted to pick a place in a cluttered environment where there are occlusions, there's some of the objects are unknown, but typically what one does is you might do shape completion for things you can't see, you find the affordances, and once you do that, you find a path. With a demonstration, it seems like it might be able to avoid a lot of that stuff. Is that fair?
So
Finding affordances, for example, or doing the shape completion.
So there's no doubt that you could take behavior cloning and do that task, right? I think there's nothing you said makes that task impossible for behavior cloning. The question would be the complexity of that, right? So we've seen surprising robustness to visual distractors that were not in the original demonstrations once we've trained multiple skills. In single skills, you could throw in some extra objects, extra clutter, and actually confuse the policy, right? So I think as the data gets bigger, then it seems that these representations feel pressure to focus on the task and ignore some of the distractors. But there's a lot of, so if you just want to do collision-free motion planning, we have some pretty useful ways to do that. I would imagine the same way we use operations space control very, very nicely. If you wanted to help the demonstrator take paths that were collision-free and avoid bumping its elbow into the table or something like this, those tools would still help. But so I think there's no question that behavior cloning could do it. The question is just how much data and how can you put the tools together to make it as effective as possible. Radhika?
Maybe related to that, there are so many cameras. Like you're saying dexterous manipulation is unsolved, we're making progress, but we're also giving it like this cage full of multiple, which I can imagine is not going to be in my household anytime soon. So like the only robot in my household is the Roomba, where the whole point was to get away with really simple sensors. Do you think it would be possible to use these same methods where maybe in the training process you have all of these cameras, but the thing that you learn only uses a restricted set in some way, and thereby in the training you're allowed to have with this thing, but then when you bring it into my house, I don't have to set up a gantry.
Yeah, that's a great question. So first of all, again, I don't think there's any fun. Okay, there is a very practical reason why we put lots of cameras, right? So having more occlusions, more partial views means that you probably need, if the human operator can do it through a single camera, right, then the task is possible, okay? I think having more views gives us more data, but also I think deals with these partial views and occlusions, which allows us to get away with shorter history buffers, right? Because we're not solving the full POM-DP, if you will. So there's practical reasons why we're doing that and benefit from it. But I think, again, that if we increase the history window and stuff like this, we've seen demonstrations where you could do the same thing through one camera. It is interesting to ask if I were to, would it help me to have many cameras at training time and then only one camera at test time? I do think it would, because I think being robust to viewpoint is something that we already put extra cameras in just to try to give some robustness to viewpoint. If someone knocks your camera, you don't want to have to redo your demonstrations. Training on multiple robot stations, getting demonstrations from different robot stations that have different camera positions helps make all of them more robust to viewpoint, for instance. So I think that could work. But I don't see the one versus many cameras as being a fundamental thing. It's more of a short-term crutch. Like, yeah, it's not like mocap or something like this, right?
It just seems like deployability is a major thing,
Yeah.
right? So like
Yeah.
the dishwasher was invented in 1886, and we're loading the dishwasher because the dishwasher is a deployable robot.
Oh, for sure. To deploy these things, you have to address those issues. But is it going to mean that the technology has to change dramatically? I don't know. I think it probably has to be matured, but maybe not. It's not a deal breaker.
We can take one last question.
Could you please emphasize a bit on the choice of the action space, because the one can be actuated either by the position of the manufacturer or the joint forces, etc. And also there are some work shows that we're using different models for predicting the future sequences. If the actions are not smooth enough, it can perform very bad. So
I just missed the very last part. If it's not smooth enough, then what?
the DP model can perform bad for predicting actions. So there are some more predicting the state sequences and use humorous dynamics model to predict actions.
I do think the choice of action space is important. We've done it in joint space. We've done it in end effector space. I don't think it's like magically you must be in end effector space. I do think that we're putting guardrails with a really good low-level controller that helps both the demonstrator and the policy as it rolls out. I think we're getting nice, smooth rollouts because of that, and I'm sure we're benefiting from that. You know, I would be optimistic that even if the demonstrations were a bit noisy, then if I had enough data, then I could, you know, still expect good things to come out. But I think that would be just an efficiency argument. I haven't seen the degradation that you speak of, but I don't deny that it could happen, and certainly in smaller data sets. So yeah, I think end effector space, operations space control, these are the things that made it work really well. But I think you could make different choices and still engineer it very carefully and get it to work really well.
All right, yeah, maybe we can stop here and thank you.
Okay.